Okay, so you all went really, really quiet, which I think is your cue to me to basically you're ready for this lecture to start. So it gives me great pleasure to see so many of you here today and online for this talk by Professor André von Schaik. André is our inaugural Furber Chair in Neuromorphic Systems Engineering, and it's absolutely fantastic to have André in our department and kind of building this neuromorphic group. Just a few bits of introduction, really, that you may or may not be aware of. André received his PhD from the Swiss Federal Institute of Technology, Lausanne, Switzerland, in 1998. He followed that with postdoctoral work in the Department of Physiology at the University of Sydney, funded by a fellowship from the Garnet Pass and Rodney Williams Memorial Foundation. Next year, he took on a senior lecturing position in the School of Electrical and Information Engineering, again at the University of Sydney. In 2011, he became research professor at Western Sydney University, so moving a little bit away, and leader of the Biomedical Engineering and Neuromorphic Systems Research Programme in the Marks Institute for Brain Behaviour and Development. In 2018, André became the director of the International Centre of Neuromorphic Engineering, and he moved quite a long way then in April this year to join our department and to establish a new International Centre for Neuromorphic Engineering here at Manchester, kind of building on a tradition that we've had. So over the course of his career, André has authored more than 300 publications, has been awarded more than 35 patents, and is a founder of 4 startup companies: Fast Audio, Personal Audio, Health Systems, and Aptera Solutions. So that's an amazing track record. It's fantastic to have André in our department, in our faculty, in our university, and I'm really looking forward to hearing André's talk today, where he's going to tell us all about 35 years of neuromorphic systems engineering.
Thank you. Thank you, Andrew. And welcome. That was a perfect summary of the talk I'm giving today as well. An overview of my career, so it's a bit of a retrospective. 35 years, I have 45 minutes, so that's about 80 seconds per year. So it will be a bit of a highlights reel, and it will be a little bit fast maybe, so we'll buckle up. See if this is connected. No, let's start with that. So I started in the area of neuromorphic engineering, actually on neural networks. This was an undergrad at the University of Twente in the Netherlands. I did my master's there. And there was a professor there, Ben Spanenberg, who introduced me to neural networks. And we were in electrical engineering, interested in making circuits for neural networks in that period, and ended up doing an internship at a company that he was involved with as well. Led to my first publication on neural networks as well. And this was in 1989 or thereabouts, and it was the height of the second peak of neural networks. So neural networks sort of invented during World War II with the McCulloch-Pitt simplified neural model. They started building some electronic neural models. It peaked with the perceptron, and then it showed that it couldn't even do an XOR problem with the perceptron. So interest waned a little bit in that area. And then backpropagation, error backpropagation, which was a method for training these neural networks, came about in the early 80s. And then during the 80s, there was a lot of hype again about neural networks and what they were going to do, and they were going to achieve through AI, general intelligence, and all sounds familiar. And so that was with these sorts of networks that only had 2 hidden layers, 3 layers of weights between the neurons that you could train. You couldn't actually do so much with it, but it had some successes, such as NetTalk, which was the first text-to-speech that worked reasonably well, image recognition, and the first beating of humans in a computer games with backgammon, with TD Gammon, reinforcement learning. But when I was working on the neural networks at the university, we already saw this coming, that yes, there's severe limitations in what you can do, and my first paper was about limitations in neural networks as well. So I sort of pivoted a little bit, not very far, I moved to, after university, I got a job at the Swiss Center for Microelectronics and Micromechanics, or CSEM, because of the French acronym. And I ended up working in the group of Eric Vito, Professor Eric Vito, was the inventor of the electronic watch. So that was quite a claim to fame. The electronic watch was invented, this prototype here for the Bulova, on 1967, the year I was born. So that's when all this started. But you can imagine that if you're doing electronics for watches, it has to be really low power electronics, because it has to run on this little battery for years and years and years. So Eric was an expert in low power electronics and using transistors at really low power levels in ways that they standardly weren't being used in those days. And he told me about those methods when I was there and I started working with it. Well, the same time that I was finishing at the university, neuromorphic engineering started as a field. It was created by Carver Mead, he was a professor at the California Institute of Technology. And during sort of mid-80s, so what, 89, he developed that field and then published his book with his student and postdocs from the lab. And that became the Bible of the field and sort of the definition of the field. We all worked with that. And we started building effectively electronic circuits that behaved a bit like neural systems in biology. Because what is neuromorphic engineering? I'm sure some of you will be asking that. It is taking inspiration from neural systems in biology and then applying that to technology. It has always had two sides to it for me, and I think for a lot of people that work in the field. The one side is the science side, is around building things that operate a little bit like biology, like neural systems in biology, to better understand the neural systems in biology, and learning about it by trying to build it. The other side is the engineering side, and a lot of the work that I'll talk about today fits more on the engineering side, is around then taking that knowledge about how the neural systems in biology work, and trying to apply that to make better technology, better widgets, better sensors, better processing, things like that. When I started, so I plotted how many publications per year you have in Google Scholar if you search for neuromorphic. So when I started, so in 1990, that was a paper every week, maybe, not even, probably like every 2 weeks or so. By 2000, it has grown to about a paper a day. Sort of. Now we're getting up to 60, 70, 80 papers a day. So back then, in the beginning, you could read everything that was published in the field. Now it's totally impossible to keep up with that. Luckily now we have AI to give you summaries of what the papers are. But this cycle, does it remind you of something? It reminds me very much of what we saw in the interest in neural networks. So where is this going with neuromorphic engineering? Are we going to get the same winter of AI happening in neuromorphic engineering as what happened with the neural network several times over? It's something that worries me, which is why I'm very much focused on applications of neuromorphic engineering, showing that, yes, this stuff works. You can solve problems with it that we cannot solve otherwise, or you can solve them better than we could previously. So that's a clear focus for me, hoping that, I mean, it can't keep growing, nothing grows endlessly, but at least that we reach some plateau of interest in it. So in the early days, when I moved to Switzerland, CSEM, and the early days of neuromorphic engineering, we were largely interested in sensors. Why? Because instead of trying to build a brain straight away, taking inspiration from neural systems, not a hell of a lot was known about how brains work properly to actually do anything useful with. Whereas the biology and the neurophysiology of sensors was pretty well understood and described. So we could start modeling those aspects. And then also, you need those sensors to get input signals that you can put into your artificial brains if you're trying to do it for time. So there's a very strong focus on building these sensors. And for vision, for instance, silicon retina. So the retina is the layer of cells at the back of your eye that light gets projected on. They have photoreceptors, and then they have several layers of neurons in your retina that process the light signals that those photoreceptors receive, and they turn that into information that, as a biological organism, we might be interested in, such as movement. Now, around that time, sort of 1992, Logitech came to CSCM. I'm sure most people know Logitech as the peripheral manufacturer for like cameras and computer mice and trackballs. And they asked if we could develop a chip that could look at a ball and tell how it was moving. Why? Because trackballs back then was used in laptops. Touchpad hadn't been invented. So since it is stripped down memory, this was the first Apple Macintosh portable, 1989. And you see the trackball there as its input device, because that was a device that you could build into the laptop. They improved it a little bit by the time Logitech came to us, but this is a 1991 model, and it became quite a standard idea to have that in the middle of the keyboard with some buttons that you could press it. But it was either a trackball or it was that little annoying joystick that's in the middle of the keyboard. It's very hard to control your cursor. Or you took a mouse and you plugged it into the side of your computer and you used it externally. But when you're on the road, this is what you have. Now, Logitech didn't like the standard trackballs they had. Why? Well, those of you that remember the trackballs and the computers and these computers from those days and the computer mice, this is how they were built. You had a ball with rubber on them, and you had, I hope you can see it in the slide, there's a wheel here that the ball touches, and when you rotate, this wheel turns, and then there's a disc on here, and when you rotate in the other direction, this would slip, but when you rotate in that direction, you're turning the wheel, and that rotates the disc, and then the disc has slots in it, and there's a light emitter and a light receiver on the other side of the disc, and you're counting pulses, and that was how it worked out, how it moved. Do we all remember the problem with it? Audience participation? Dirt, exactly. So you have to clean these things. Like every week or two, you have to take it apart, take the ball out, clean the ball, take it like a Tipex and get the gunk of the wheels and so on. And that's with a mouse that runs on the surface of your desk or on the table, presumably reasonably clean. If you use it as a trackball, you're touching it with your fingers, you get skin grease on it and so on, they would get dirty even quicker. And the balls were even smaller, so the curvature of the ball was higher, which made the contacts smaller and so on. They were trouble, basically. So nobody liked these trackballs. Nobody likes the joysticks either for the laptop. So Logitech was thinking, okay, we just look at the ball, we won't have that problem. Even if the ball gets dirty, if it's a random pattern, then it doesn't really matter so much. And that's what they asked. So we did that. And it came on the market in 1994, and Logitech started producing these. But remember this fellow that started Neuromorphic Engineering? So he also started a spin-off company in the early 90s called Synaptics. And the first job of that spin-off company was, again, with the Neuromorphic Engineering company, was to do handwritten digit recognition for checks. You pay with the check, particularly in the US, and then the register would have to register the amounts and so on that was written on the. That's a separate story that I won't go into today, but that didn't become a commercial success for them. What did become a commercial success for them, they developed a touchpad. And so that came also on the market in 1994, which means that Logitech actually never ended up putting more trackballs in the laptops because the touchpads were way easier for laptops. One of the big reasons I think is, well, one is we're well used to how they work now. But if you put a trackball in your laptop, the laptop has to be thicker than the ball. Otherwise, the ball's going through your screen. And so that means your laptop has a minimum thickness that's much thicker than when you do a touchpad. So that's why touchpad makes much more sense in these laptops. And it's now pretty much all laptops use, right? But Logitech did make them as products, but desktop trackballs. So you put them next to your computer and use them. You see them a lot used, for instance, in clean rooms or places where there's little space around where the computer is, basically, but where you still need human input. I think clean rooms for where they fabricate microchips, they also like them because they generate less dust, because they're not rubbing on the surface. And they did this for 30 years. Up to last year, you could still buy these Logitech trackballs. Now, you might find one on eBay, but it will cost you a lot more than it cost you last year. But they're running out. And I think that's because they run out of chips. Because this was done in a 2-micron process back in 1992. And there are no fabs anymore that do come with 2-micron processes. And because the technology is all shrunk, so they haven't made anything. Okay, so after the Logitech project and some other silicon retina stuff that I've worked on, I ended up deciding I wanted to do a PhD. So I moved to the EPFL. Eric Vito, the boss of the team that I worked in at CSEM, he was a professor at the EPFL as well, so he became my PhD supervisor. And I started working on sound, so I switched from vision to sound, studying how the ear works. And we built models of hearing in biology, and that was starting, for instance, with a silicon cochlea. So the cochlea is this coiled structure in your inner ear that receives the sound. So your eardrums, we've learned, has these 3 bones in your middle ear, and these bones, they press on the membrane in the cochlea that sets up vibration. So if you stretch your cochlea out, you can't, it's a bony thing, but if you imagine that you can do it, then it has this membrane in the middle, and this membrane is stiff at the start and floppy at the end. What that means is that high frequency sound vibrates most here, and low frequency sound vibrates most at the end, and then it passes. And then you have the structure on that membrane with these cells called hair cells, because you've got these little hairs sticking out. And they're the ones that are sensing the vibrations and turn those vibrations into an electrical signal that becomes the nerve pulses and the auditory nerve brain receive. And this, the frequency spacing here is a little bit like notes on a piano. It's sort of laid out like that. So I've built a model here. So here I have a little with a cochlear model and putting some music through it. I hope it's a little hard to see with the lights on here, but this is model of the vibration of that membrane, and then here it's just showing the energy of the time of the song. And you see the vibrato in the voice, for instance, how she hits the notes from the way up, and so on. So we started using that as our preprocessor. So we did chips for that to make the sound. This is the software model that I did much later. Back then, you couldn't run something like that on a laptop. You actually had to make a chip that can run it. Now you can write something in Python, and if you write it cleverly, you can get it from the laptop. After doing the cochlear, which is just the input of the sound, converting sound into nerve pulses, started looking at, okay, so what does the brain do with that sound information? And I got really interested in that. And just around that time, there were 2 books that sort of new books that became my Bible for a little bit during my PhD. They were the Springer Auditory Handbooks in Auditory Neuroscience. And one was the neuroanatomy, and the other on neurophysiology. Neuroanatomy tells you what things look like, basically, not much more than that. Neurophysiology tells you about the electrical signals of the individual cells, but not what they look like. And as an electrical engineering PhD student, it was actually quite hard to figure out, because they even give them different names to cells. So they tell you what this type of cell looks like here, but then you don't know what cell it corresponds to. That's and neither of those books tells you what it was there for. It was all descriptive about this is what it does. But and this is what it looks like, but not like this is the function it is. And for that, I got in touch with Ray Meadows. He was a professor in University of Loughborough here in the UK. And he was a modeler of the auditory system, but like a theoretical modeler and computer modeler. And he was the guy that I really needed to interpret that. So he became sort of the, yes, this means this, yes, that means that, and it probably is this, but he wasn't an engineer. So as a team, we did some really nice work together during my PhD. So he became a co-advisor. And one of the things I built was he made a model of pitch perception, how we hear how high sounds are, like how high the singing voice is, for instance, in the previous demo that I did. And I built that electronically, and I built some other auditory models. And they became part of my PhD thesis of analog VLSI building blocks. So analog VLSI just means electronic building blocks for the electronic auditory platform. And I actually got about 10 years later, something published in one of the later versions in the same series that I started with, which was really nice way to close for that project. So then I moved to the University of Sydney after that to do a postdoctoral research fellowship. I went to Sydney for 2 years. I moved to Manchester 27 years later. So I ended up spending in Australia way longer than I thought I was going to. And one of the things that I really started looking into there was still with audio sound localization. How do we localize sounds? Well, one of those things is that if a sound is coming from that direction, it reaches this ear before it reaches that ear. So there's a time difference between them. And it's also typically louder in this ear than in that ear because it's a bit further away to that ear and your head is in it. And we use those binaural cues to get a sense of direction of where the sound is. And quite early on, when I started as a senior lecturer in electrical engineering at the University of Sydney, we started building these chips that did sound localization based on these binaural cues. I mean, these actually had 4 microphones in it, tiny microphones for those days. And the idea was just for the puck, that you could drop in the field and have multiple around, and they would do space or situational awareness by the sound of where things were coming from. So it would tell you where vehicles were based on sound localization. So that was a very large project we started with. But the binaural cues just tell you about this. There's actually this whole virtual cone, which is called the cone of confusion, where anywhere on the cone will give you the same time difference and the same level difference between both. Because the path plane is different. And so that makes it ambiguous. Once you know roughly where it is, but you don't know where it's in front or up there or behind, and also not how far away it is. So for that, we use binaural cues, our ears. And ears are different for everybody. There's an individualistic fingerprint. So you can use them for biometrics as well to recognize who it is. And what happens with your ears, if the sound is coming from there, it hits these cavities and ridges in my ear at a different angle than when it's coming from there, or from there, or from there. And that sets up resonances and anti-resonances, so it changes the spectrum of sound that reaches your ear. And our brain interprets that not as a change in the sounds that the source makes, but as a change in the sound's position, if you do it right in a way that is consistent with your ears. So we started recording ears. We put little microphones in your ear canal, or various people's ear canal. And then we have, this is not a giant pair of headphones, it's actually a robot arm that has a loudspeaker here that can move anywhere a meter away from you, basically. And so then we could measure from like 400 positions in space the impulse response of the ears. How do the ears feel for that sound? And that then allows us to do the following trick. If you listen to sound over headphones, if you pay attention, you probably notice that it sounds inside your head. Sounds might sound more to the left and to the right, but they don't sound external to you. And that's because you're bypassing these cues from your brain. You don't have those anymore when you play over headphones. Whereas in free field, you do have that. So if you can pre-filter the sound that you play over headphones with your ears transfer function, then you can make it sound as if it came from out there. But that's individual. Everybody's ears are different. So everybody needs a different set of filters for that. We had enough recorded ears, pairs of ears, about 200 or so, 250, that we could start making estimates of people's ears based on listening. So one of the companies that Andrew mentioned at the start was called Personal Audio, which would do over the internet sort of listening tests with your headphones on, would estimate the cavities in your ears, how your ears change the sound, and then learn to apply an approximation of those filters to make the sound out there. We got that working, we got a product out, but the problem here was 2007 to 2010. Nobody wore headphones. Computer games. I mean, it's almost unimaginable now. Now you look around, people are wearing headphones all the time, everywhere. Back then, it was almost pretty much computer gamers with wired headphones into their desktop computer or their gaming computer. And they were the only ones that were interested. This is clearly a company where we just learned. If we'd done this even 5-6 years later, we would have made a lot of money, but we didn't, so we didn't make any money. It's actually a lesson there, because we have some technology that we protected as well. And if you start protecting it, it starts costing you money. And then if you're too early, you don't have money to keep paying for the protection. And then it becomes public. Then anybody can use it. So don't be too early. Don't be too late either. Another company that I did in that day was Fast Audio, still with the audio, for hearing aids. So I told you about these monaural cues that tell you where sounds are outside. When you put hearing aids in, again, the sound doesn't go through your ears normally. It's either you have your receiver behind it with the microphone that gets the sound there, but they started developing these little ones where they're totally in the canal. So the microphone is still in your ear, and the sound goes through your ear, so there it should work. But because these cavities are pretty small, most of the resonances are above 8 kilohertz. And as you get older and you get more deaf, the high frequencies are the first thing to go. So you can't necessarily amplify that loud enough with these little hearing aids, or even with the bigger ones, to make it audible. So the trick we found was to virtually make your ears larger. So there's cavities and there's resonances and anti-resonances would be at lower frequencies. We virtually made your ears 2 or 3 times larger. And it looks silly, obviously, with 3 times larger ears, but this was all done virtually. And then your brain would learn those new ears, because your ears change during your life anyway, they keep growing, for instance. And so you learn your new ears over time and decide working. So that's in hearing aids, but that started in 2000. I think they came on the market in 2021. They started hearing aids. That's how long it took to get anything in hearing aids. Okay, so those are some highlights from the University of Sydney. And as Andrew also mentioned before, in 2011, I moved west to the University of Western Sydney. It was called back then. And I had the opportunity there to set up a group that was going to try and combine the electronics and the neurophysiology to do all those things together. So we had neurophysiology, there was staff at the School of Medicine, part of my group, computational modeling that we were doing, or computer modeling of how the biology worked, neuromorphic engineering, making hardware. And if you do this pathway and you hire engineers into your group, you're basically learning from biology and applying it in technology. You're also going to get engineers that like to take technology and add it to biology, which is biomedical electronics, people doing biomedical. So that was quite a good combination of things that I thought it didn't work so well. Actually, I thought I had a great plan, but it was one that didn't really work. It was very difficult to get grants that spanned get funding that span neurophysiology to electronics, because people assessing it, they would only know about one bit or another bit, and not all of it, and not get all of it. I didn't have a track record in this either, and I'm the lead applicant or something like that. So it was difficult, it didn't really move. One thing coming up next, totally irrelevant, but nobody believed me when I say we had kangaroos on campus at Western Sydney nearly every day. So that was a really good thing to come to work. I also started building computers that were acting a little bit like the brain. So trying to model how the neurons in our brain process signals. The neurons in our brain, they send nerve pulses, we call them spikes, to each other, and they do the computation based on that. We started that project in 2014 in that group, and I'll get back to Deep South in a little bit. So because it wasn't working so well, we relabeled this to biomedical engineering and neuromorphic systems in 2016. Also note the university rebranded itself and paid the consultants to go from University of Western Sydney to Western Sydney University. And that's how these rebranding campaigns go. So we still did neuromorphic engineering, so try to do neurophysiology, the biomedical engineering has become a bit more important in it too. And otherwise we just move some blocks around. I wanted to show one application from the biomedical engineering. One of the things that was developed was a shirt that had multiple elastic bands in it, and those bands can change their resistance as you stretch them. And you could use those to determine heart rate and breathing patterns and so on. So it was a wearable piece of clothing that you could get to monitor people, respiration, cardiac stuff, and also blood flow. The one thing that did become really important for us that we started doing back then was putting these silicon retinas on the telescope. So here's 3 telescopes on a mount that's pointing the telescope. Actually, there's a 4th they call a finerscope. It's the little one that you look at. Here's a silicon retina. Here's another silicon retina. And this was a standard astronomical camera, much bigger than we were working with. And for our first recordings, we were just trying to see what we could do with that. And so we recorded a bright star, and this is for you, it's the first data you see from one of the silicon retinas. So where it's blue, the camera is telling me it got brighter, and where it's red, the camera is telling me it got darker. That again. And where it's black, nothing changed. And since you're looking at a mostly empty sky, there's a lot of places where nothing changes, so you don't need to get signals from it. Also, if you look carefully, you can see in the center of the star, and it's not jiggling around too much, it's actually also black. If they have always right, nothing is changing, really. Enough. It's around the edges because it's a star twinkle that you see. And we're playing around with that, trying to find another star or something like that. And then all of a sudden, hey, what was that? That was moving way faster than the star would move. And we already controlled the airspace there, because this was done at an airfield. And we knew it wasn't a plane flying through. And we're focusing at infinity, basically, long distance. So it can't be an insect flying nearby, so that would be in focus. So we worked out, okay, that's a satellite that we saw. That's how we got into tracking satellites with these event-based cameras. So then we learned how to track a satellite. So here, the satellite here is moving a little bit in the field of view. Here we're looking at it with time going in the vertical direction. So we look, and we're starting to label the events that belong to the object that we're tracking. We learn how to do that. We learn how to do it with multiple objects simultaneously in the field of view. So here we're tracking a rocket body or a star, actually, because here are some satellites flying through in different directions. And so we learn how to do that with multiple ones. We learn as we're tracking here, this is the rocket body we're tracking. You can't really see the thing we're tracking, but you can see the stars sliding through as we're doing it. So we learn how to automatically extract what are stars, build the star map from it, and so on, tracking that. And all those things over the years that were there. And then in 2018, we got funding from Royal Australian Air Force to put that in a mobile system, basically converted shipping container. This was an idea that my colleague Greg Cohen, who's now the director of the International Centre for Neuromorphic Systems at Western Sydney, had at the time. We sketched on the back of a boarding pass, presented to them, and got funding for it. So that was the shortest run I proposed for having this. But we also only had like 5 months or something to build this. So it's a shipping container with a lifting platform in it that lifts the telescope out, sliding roof, so that the telescope can come out. And then you can deploy this thing at various places and start looking at stars. The fact that it's mobile was really useful. This was Apple Air Show in 2019. We all know what happened at the end of 2019, 2020. COVID happened. So during COVID, this system could work at home. So I put it in my backyard. That's easy to move shipping containers around, right? So there's a whole industry that does that as a job. So that was easy. And yes, this is the house we gave up to move to Manchester. I hope you appreciate you being here. And so we continued experiments basically from our backyard. And then in 2022, the second one, this one is a bit loud, isn't it? So we built the second one and we deployed that at the observatory in the Australian desert. And you can see this rain never rained in the desert, but we put an optical telescope there to look at stars and it started raining. And we can also tell these things with rainmaker. So they dried up really quickly. So we can set that up in like the same day. Basically, you just unpack it, set it up. It needs a few hours of a clear sky, calibrate itself with the sky, and then it's ready to go. So you can move this thing anywhere you want. And last year we had one in the UK. The UK Space Command used for a while, and they are now getting some more from us. We hope they're the next startup company that will get to the moment. Also, we were learning to localize the satellites that we were extracting by the star. So again, I hope the contrast is good enough here. So we automatically extract where the stars are. And stars are fixed positions in the sky. They have a coordinate system called right ascension declination, and each star doesn't move, at least not on the time scales that we care about. It will move over tens of thousands of years, but not in the time scale that we care. And then anything that doesn't move like a star is an object that we might be interested in, a satellite, a piece of space, and we can localize it very accurately and very fast with respect to the stars. We build a nice web interface around it, so I can operate this remotely. I can operate it from here, for instance, the one in Australia, which is convenient because I can run an Australian night during the day here, for instance. And also a web interface to look at the data. So here, this is an object that is clearly blinking very, very brightly. You can't see it because of the light above me, and I don't actually know how to set these light scenes. Let's see, there we go. So there's actually a second object here. If I point it out, you probably see it. So there's two objects in here we extract and find and so on. So you can look at this online, and we can sell this data to customers who are interested in tracking their own satellite and see if anything else nearby is. During that period, I set up the International Centre for Neuromorphic Systems. Western Union started in December 2018, so let's say 2019 simplify it. And we took these original boxes that we had. You remember those from a few slides ago. Basically started looking at, okay, we work on sensors, we work on signal processing, and we work on neuromorphic hardware. That then looks at the mission statement, so we put a bit of graphics effort in it. And so we work on sensors, hearing, vision, also other sensors. We've done some work on electronic notices. We've done some work on tactile sensing as well. Algorithms, because you need to take the data that comes from the sensors and process it to make sense of it. And then processors to run that on. But again, at the top there is applications. So still a focus on trying to get stuff out there in the real world for real tasks. One of the things we did, and one of the coolest things in my view we ever did, was we got payloads on the International Space Station. We actually have 2 active payloads on the International Space Station. The first one went up in December 2021, and it was meant to only work for 12 months up there, and then normally they dispose of it by burning it in the atmosphere, so you don't get your reach back after you've built it. But they liked it so much that they kept it up there, the data that they're getting from it. They just had to move it in July last year or so to a different side of the space station. So originally we were looking down and at the horizon, and now we're looking up and at the horizon because it's moved to the other side. Whereas this new one went up in April this year. It's a much bigger package. It's looking down and at the horizon now. And it's a much higher resolution camera. The original one was a very low resolution sensor that we have. This, we're looking at the ground, as a resolution of about 300 meters per pixel. So you can only see big things, really big things. This is the resolution of about 7 meters per pixel. You can start seeing trains and ships and aircraft and thanks. So you're all awake now. So yeah, that's the new one that's up there, and we're really happy to confirm that one works well. This is some data from an old one. The yellow dots are the data that we've extracted. This is looking at the horizon when flying above Harbin in northeastern China, for instance, and looking at satellites. And when you're at the orbit of the satellites that the International Space Station is at, and you look in front of you, it's almost all Starlink satellites. There's so many Starlink satellites in the orbit now, and it's amazing. So to commercialize some of this, Western Sydney University and also the inventors, we spun out Optera, and Optera will commercialize these astrocytes that I told you about. It's the first product that we'll be selling, both as containers for people that might want to use them, but also create our own network and start delivering data that customers might want about particular satellites or their own stuff. We're working also on space payloads, because it is clear that you can do this tracking satellites from the ground, but you're always subject to weather. If it gets cloudy, you can't see. During the day, you can't see very well with it either. Although we do have some evidence we can see some things during the day, but we're still investigating that. But it's clear to me that this will go to space. I predict that we will have self-driving satellites in space before we have common self-driving cars on the ground everywhere. It's a lot simpler. There are no kids kicking footballs across the street and things like that. So, but it's necessary. It's getting so busy there that satellites need to be able to see what's around them and need to be able to act on them. That's another thing, and then we're making our own sensor chips to put in these packages as well. That's sort of what Optera is working on now. And Optera started out of Western Sydney, but its current plan is for it to move here to Manchester later this year. So we're working on that in the background as well. So some other application examples that we worked on at the International Centre for Neuromorphic Systems. using the sensor to look straight into the sun here, and there's a drone hanging there. So normally if you look straight into the sun with a camera, you can't see anything. These sensors have really high dynamic range, and as the rotors are spinning, you can even extract how fast they're spinning with the cameras are passing. So you can get an idea of how many RPM each of these rotors is putting out, which you can then start predicting how the drone will start moving and so on. You can imagine everybody's interested in tracking drones and predicting their movements. Another one, practical instances are here, right? We did a system for koala detection and monitoring. This is a package where we have an audio package sort of with stereo microphones. It is detecting koala calls and recording them, but it's recognizing whether it's a koala call or not. So you can leave this thing in the forest for months at a time to operate on the battery. When you come back, it will just record the koala calls and ignore everything else, and it will give you a tally of how many koalas there are. That's the thing that you need to do before you do say development, if you're planning to cut down forests, but also mining companies in Australia have to do it when they're building mines. They also have to counter it with regeneration efforts, and they need to show that the regeneration efforts are working, so they need to be monitoring. And the way that was standardly was done was just get a guy who knew about koalas listening for a while to tell you whether there are koalas there. This is a bit more advanced, I guess. So that was a nice thing that is a product that came out as well. Also some localization with 5 hydrophones under a boat, basically, just listening for, oh, that's going to be funny on this display, but just listening for sound on the water to tell you from engines where other ships are, basically. It's a bit like sonar, but passively. You're not pinging a signal out yourself. And then Deep South that I mentioned earlier. So this is, people here know about Spinnaker. This is sort of a Spinnaker version we built in Sydney and a customer down under. And I started the project when IBM True North was a high-bit power in the Deep South. And this is in 2024 when we got the system running first, but we're still working on this. It's now 11 years basically on this project to build this, and we're still trying to get everything to work nicely. I've predicted a few times before that it will be up and running. I'm still hopeful that we can get it up and running fully this year, and then start deploying neuromorphic workloads on it. Basically, simulating how brain process signals. And the big thing, well, a couple of big things, but the big claim that will help get the publicity is it will do 220 trillion sparks per second processing, which is about what's estimated your brain does, human brain. And it will do that in real time. And that's orders of magnitude more than other systems are doing at the moment. That's the first time we should be able to do that. Second thing that's important about it is it's all commercial off-the-shelf hardware you can buy. It's just uses this reconfigurable hardware, these FPGAs that you can program to be connected differently, effectively, to many different circuits. And by doing this, we can build this thing, but it also means you can scale it up or down, depending on how much money you want to spend on it. And it also means anybody else can make a copy of it. And that's often been like with Spinnaker 1, Spinnaker 2, Intel at OE, IBM at True North. That was all special hardware. And that meant there's, just like the Logitech chip from my Fractal, there's a limited supply of that hardware that you can get. And then they never become products, and other people can't go ahead and buy it. So with Deep South, we'll make this open source as well, the design and what components you need. So we hope that other people can start building these systems too, and start contributing to it and using it to study how brains process these spikes and make sense of it, how to do things effectively, because that's still a big open question. And part of the reason that's such a big open question is it's so hard to simulate on the computer. You can only simulate very small networks. They don't necessarily tell you what big networks are doing. So I'm hoping also that this will be a little bit like what the GPUs were for deep learning, for those who didn't know about it, the graphical processing units that made deep learning possible, and the current wave of progress in AI. I'm hoping that this hardware will make it possible for the spiking neural networks to process the data more like the human brain. And so then in April this year, I moved here. So I had to do some changes. Just adapt the color scheme a little bit. I'm not too certain about the color scheme yet, but that is there. So I don't really have much to tell you about here, other than that, what I'm planning to do, which is very much along the trajectory going on with the center in Sydney, which is what this is suggesting to, and in close collaboration with the team. And I still know the guys really well. I still want to work with the guys. I want to have another team here, and we can collaborate across the globe, basically. We need another team in the US, I guess, and we never have to sleep, right? You could work around the day quite easily. So that's the plan here. So I hope I've given you a flavor of the things I have been doing and the things I'd like to go and do. So now I'll open it up for questions. Thank you.